In simulation, you will be using the same velocity analysis data for comparison. Okay, so I'll be going through in detail about the assignments. Come. Don't sit alone. Sit in groups. I think there's a big traffic jam, so I'll just wait for another 15 minutes. So I think this is due to the F1. Probably this assignment is going to be the most difficult assignment for the entire program. So this is going to be the most challenging one. Tips. I'll be discussing A to Z. As I said, everyone, the dimensions are different, so your drawings will be different, your answers will be different, but the step-by-step process is the same. So when you print and submit this assignment can go up to 70, 80 pages. Part 1, part 2 together. So it requires some amount of CAD. If you know CAD, then it is much easier. So you can use any CAD software for most parts. But for the last part, you must use the working model. So working model, it is something like this. You have a mechanism, okay? So the dimensions of the mechanisms are different for all of you. Okay, you are analyzing the mechanism in different ways. So first, you are going to analyze the mechanism by graphical method. Okay. Then you are going to analyze the mechanism by analytical methods. Then you are going to analyze the mechanism by simulation. So the simulation can be done by working model, or if you want, you can also use other software. Okay. But the basic software you can use is working model. All right. Okay, so we start now. The first half an hour, 1 hour, 1.5 hours, I'll go through some slides. So later on, we will go into the main drawing part. So the position analysis of a mechanism. So what is a machine? So all of you know, right? So machine is used to perform some functions, right? So it's basically a device, and when we speak mechanically, so it is to transmit and direct forces to achieve a specific object. So you can have a slider. You've done one mechanism in your engineering done slider crank. So basically a slider crank is a mechanism. So it performs, okay, a rotational motion is translated into a linear motion. So the crank rotates. So the piston translates. So So it's basically a mechanism. So when you look at a mechanism, so there are different parts of the mechanism. Okay? So basically, if you see here, there's a motor here that transmits. There's an actuator here. So there are legs. Okay, and there's a base which is not part of the mechanism. So there are different parts in a mechanism. We can analyze the mechanism or a machine, okay, in different ways. The first part is the kinematic analysis. So kinematic analysis, as you know, is a description of the motion. So we need to understand in terms of first describing the motion. How many links are there in the mechanism? So what is the degree of freedom of the mechanism? So we define what is meant by the degree of freedom. Okay. So if you look at this table which can lift, okay, you can consider the significance of the length of the legs, okay, to support this platform, okay, and whether the legs needs to be crossed or you can have vertical legs or the arrangement of the legs, the description, how the arrangement of the legs will influence the lifting, okay, and also how far must the cylinder extend to rise the platform, that is in some inches. Okay. So kinematic analysis is description of the mechanism, and also we try to link if there are any relationships in terms of the distance and the degree of freedom. After this, we look into the dynamic analysis. So this is where we are going to analyze the mechanism in terms of forces. Okay. Now we bring the forces which performing the activity. So the basic mechanism. So what should be the maximum force you need to use? Okay. What should be the minimum force that needs to be used? Okay. Then is there any momentum applied on the mechanism? That means, is there a possibility of tipping the mechanism? So the forces, act in different directions, so there will be movement will be developed. So what is movement or the moment of force? So moment of force is basically rotates the objects, right? So here we need to analyze the forces in such a way that is there any possibility that the mechanism can be. So all these things comes under the dynamic force analysis. And also here you will be studying what type of materials that can be used to support the legs. So that means what is the net force acting on the legs. All right guys, I think some of you join later. So it always helps you to sit at least two together, because you need to draw mechanisms later, and you can always learn from each other. Okay? And I was telling you at the beginning that this course is very hands-on. Okay? So you can learn a lot in the classroom because my teaching is very limited. So I'll be just telling you how you can do the different types of graphical analysis. And you can only learn if you do that in the class. So once you go back and try, you will find it much more difficult. So it always helps sit two together at least minimum. Don't sit alone. All right. So kinematics basically deals with how the things move, the description of the things, okay, movement. And here we define the position, displacement, rotation, speed, velocity, and acceleration. Okay. And under kinematic analysis, we look into the geometry, so the length of the links in the mechanism. So the geometry is very important part of the mechanism. So the very first thing we are going to do is the position analysis. So for any mechanism, the first thing we start is the position analysis. So we'll discuss the position analysis on some time. So under dynamic analysis, where we bring the concept of the force. So what are the forces acting on the mechanism, and what is the effect of the forces on the mechanism? Okay, so when you do your assignment question, so you are going to simulate the mechanism in working model 2D. So when we talk about mechanism, so some terminology which we'll be using is the linkage. So what are the various links connected to the mechanism? So what is the frame? So frame is that portion of the mechanism, so which is not part of the rotation, which is not part of the movement. So frame is something which is fixed. Alright? So the links, rigid body, what is the concept of rigid body?
Cannot move. Cannot move.
No. The concept of rigid body is when you have a mechanism when it is subjected to forces. So we know under stress analysis that there is stress and strain and there is deformation of the body. So the rigid body means we assume that there is no deformation in the body. So that means the stress and strain are invisible. Okay, so the rigid body means that the mechanism we consider rigid body in the sense we don't consider the effect of stresses and strains on the system. Okay. So the first part is the mechanism will have links. So what is the links? So these are connected with other links to transmit motion and forces. So for example, a simple slider and crank mechanism. So you have a crank which rotates. So then it is connected to a piston with a connecting rod. Okay. So basically there are 4 links in that. The piston itself is a link. So the piston can move. Piston is connected to a crank. Okay. So there is a connecting rod. So this is the concept of rigid body. Basically, a true rigid body does not change shape during motion. So that means the effect of stresses and strains are negligible. Okay. Now, a linkage, when we talk about links and linkage, so a linkage is a combination of links. So when we talk about linkage is where rigid parts are connected from a chain. So that is the linkage. So these linkages are the basic building blocks of mechanism. So these linkages are made up of links and joints. For example, here you can see this is a binary link, means it has 2 links. Right? So this is a ternary link, 3 links. So this is a quaternary links. So you can see these are called as nodes. So this is where you can have joints. Okay, so the frame of the mechanism is the rigid part, so which is not part of the exhibits and it is not part of the motion. So it exhibits no motion. So for example, the base here you can consider as the frame for the mechanism. So you can see this is a cross trainer. Okay. So there are many moving parts in this, but the base is where, okay, no motion exhibits. So the base sits on the ground and remains stationary during operation. So can you see clearly or shall I switch off the light? Okay. Alright. So then when we talk about the joints, so these are the important things. So we can define a joint as a full joint or a half joint. So a full joint or a W joint, it can give pure rotation. Okay. And you have a sliding joint. So this is the sliding joint, so it can provide motion also. Okay, so here the free joint can provide motion, rotation. It's a pure rotation, it's a pure translation or linear motion. Okay, so you have hop joints, or these are hop joints are also known as the higher order joints. Okay, so they allow rotation. For example, you have a cam joint, you can see, and a gauge joint. So they are called as higher order joints. So they not only allow rotation but sliding. So a combination of sliding plus rotation. So whereas the full joints are only a pure rotation or pure translation. So it's a pure horizontal motion or it's a pure rotation. Whereas a hop joint is a combination of these two. So so higher order joint or half joints. So both rotation and sliding is performed. Okay, so the motion between links can be sliding. So for example, a slider crank you have seen, a piston and a crank. Okay, that is sliding. So you can have pure turning, so for example a wheel on axle, or it can have a slow motion such as a nut and bolt. So a crank is a link which makes a complete revolution and is pivoted to the ground. So for example, so this one you must have done during your engineering dynamics. Okay, so basically you have a crank like this. So this crank can rotate 360 degrees. So this crank will have a circular motion. Okay, so this is the crank part. So now the crank is connected to through a link. Now this is a pin joint, so it is connected to a link. So this, let us say, is a piston. Okay. So this piston can, so depending on the rotation, okay, so the piston can move either way. Okay, so when the crank is here, and the crank is here, so probably the piston will be somewhere here, let us say. Okay, when the crank is here. So when the crank is here, the other side, okay, so probably the position of the piston will be like this. Okay, so this is the connecting rod. So we can call it as a link basically. So basically this crank will have a circular motion, rotation. So this crank is connected to the piston here, so the piston can have horizontal motion. So this is basically a slider crank mechanism. Okay. I go back to the slide. So the crank is a link. So for example, we're seeing the connecting rod in the example is the crank. Okay. Okay. Crank is which can make complete revolution. So it's connected to a motor. So the motor can rotate the crank in 360 degrees. So a rocker is a link which has both oscillatory motion and is pivoted to the ground. So a rocker is a different type of a link. We can have a look at the rocker later. Then you have a coupler. So this is a connecting rod. So this is a link which has complex motion and is pivoted to the ground. So the example I've shown you is this is the same thing. Now you can see this is the motor. So this is the crank. So this crank can move 360 degrees around. Okay. So this is a coupler. Okay, this is a round, and this is basically the ground. So this is a fixed ground here. So this is also the fixed ground. Okay, so this one is something like frame. So there is no motion. So frame, sometimes you can see there is a physical link on the call just as a ground link. Okay. So the link is not part of the motion. So it is not part of movement. Alright, so we come to this condition. What you see, can you figure it out what is meant by S, L, Q, and P. Can you look at this S, L, P, and Q? So S represents here the shortest link in terms of length. So S is the shortest one. L is the longest link. So when a system is consisting of links, okay, when a mechanism is consisting of links, so for the system to act as a mechanism, that means, so there must be a complete rotation and the mechanism must have a movement. So then the shortest length plus the longest length in the mechanism, the links should be less than the length of the two remaining links. So P and Q are in between the short and long. So S is the shortest link, L is the longest link. So for a mechanism to work, so the total length of the shortest link plus the longest link must be less than the total length of the remaining two links. If this condition is not possible, so that means there is no way the mechanism can move. So that means when the rotation will cause, the links will collide on themselves. So for any mechanism to work, okay, the total length of the shortest length plus the longest link should be less than or equal to, okay, the total of the two remaining links. So this condition is known as Greshoff's condition. We will see a bit later also. Yeah. Now for any mechanism, so we have what is known as degree of freedom. So you must have studied a bit about this in engineering dynamics. So degree of freedom refers to if you want to describe the mechanism, so what are the minimum number of coordinates required to describe? So that is known as the degree of freedom. So it is the number of coordinates required to define the position of the system at any point of time. So what are the minimum number of coordinates required to describe the system? So we can have this equation known as the Douglas equation. So which tells you that for any mechanism, the degree of freedom is, so 3 times, we may just note down this, 3 times L minus 1 minus 2J1 minus J2. So this equation you will not be using in the exams, but just to begin with, to understand the concept of degree of freedom. So here L refers to the number of links. So a mechanism can have many number of links, right? The total number of links in a mechanism we call as L. Okay. J1 refers to the number of full joints. So we see what are full joints. So full joints are the pin joints and the sliding joints. And the higher of the joints, G2, are the number of hop joints. So the hop joints gives both the rotation and linear motion. So for a mechanism to understand the degree of freedom, so this is the formula we use. 3 times L minus 1 minus 2 times J1, number of full joints, minus J2. So J2 refers to the number of hop joints. Now, so we'll try to understand the degree of freedom first. Now, if you see here, this is just a pencil. So you want to describe this. So to describe this, how many coordinates are required? So in rectangular coordinates, you need to know the x, the horizontal displacement of this, okay, with respect to your coordinate axis, capital X, capital Y. Okay. So you need to know its position along the x-axis. You should know its position along the y-axis. And also you should know its orientation. So if you want to describe the position of this particular one in the rectangular coordinate system, you need to know its x coordinate, you need to know its y coordinate, and also you should know its orientation. Okay. Now we know that the theta we treat it as positive if we measure from positive x-axis counterclockwise. Okay. So this theta can be positive or negative. Now tell me, what is the degree of freedom here? So is it 1 or 2 or 3? So the degree of freedom is 3 here. So x coordinate, y coordinate, and the orientation, the angle theta. So if you want to describe the position of this, you need to tell in terms of our reference system, okay, x coordinate, y coordinate, and also the angle with respect to positive x-axis. So the degree of freedom here has 3. X, y, and theta. So, for example, if you see here a rolling, a rotating full pin, okay, the joint here. So here, and this one is just a sliding joint. Okay. So here you can see the degree of freedom. If you know the angle, that's enough to describe the motion here. Okay, rotational angle theta, or angular displacement. So here you know only linear displacement, that's all. So there's no y coordinate, there's no angle. So the degree of freedom for both cases is 1 degree of freedom. Okay. So these are the full joints. So you can see you can reduce the degree of freedom. So for a simple pencil, the degree of freedom is 3. But now for 2 links connected with a pin joint or a slider joint, so the degree of freedom is only 1. Now here, this is a roller slide. So in this case, it has both linear displacement and angular displacement. So the degree of freedom is 2. So similarly here, the degree of freedom is 2. Now this is a revenue joint, angular displacement only, the degree of freedom is 1. So this is a prismatic joint, degree of freedom is 1. So this is again helical joint, so rotation, angular displacement, degree of freedom is 1. Okay, so now here 2 links are connected, okay, 2 links are joined, so there's only the degree of freedom is 1. Now you can see here there are 3 links are connected, okay. So you need to know the angular displacement for link 2 and link 3. So the degree of freedom in this case is 2. So that means you need to know 2 coordinates to describe the motion when 3 links are connected. Okay. So in this case, you can see a planar joint. So here the motion can be in 3 dimensions. So along x, along y, or it can have a rotational motion. So in this case, the degree of freedom is 3. Now this is a spherical S joint. So again the degree of freedom is 3. So that you need to know the position along x, y, and z. So now, so basically now why we need to know about this degree of freedom, okay? We'll see in the next slide. So we can describe mechanisms as open mechanism and closed mechanism. So it's an open mechanism chain and a closed mechanism chain. So we can have mechanisms both either open mechanisms or closed mechanisms. Now, we have seen that each link, the degree of freedom is 3. So we need to know the x coordinate, y coordinate, and the rotation, the angular displacement. So similarly for 2 links, when you want to study separately, so the degree of freedom is 6. So 3 for this link and 3 for this link. Okay. Now when they are connected by a full joint, okay. So now the degree of freedom is with respect along x, y, okay, the position of this pin, and the angular displacement of the links. So the degree of freedom is 4 when they are connected by a full joint. Now when they are connected by a roller or hop joint here, the slide joint, now you can see the degree of freedom is the displacement of link 2, the displacement of link 1 along x-axis. 2, then the position of the horizontal link along y-axis, then the angular displacement of the 2 links. So you can see the degree of freedom in this case is 5. Okay, so that means what we can understand is how the links are connected, so the degree of freedom can vary. It all depends on what type of link, a full joint or a hop joint, and how the links are connected. Okay, now for example, you can have a look here. So there are full and multiple joints here. Now this is basically a mechanism. Now you can see there's a sliding joint here, and this is a ground here. Okay, so this is a ground. Now this is ground. Okay, now for all mechanisms, ground is considered as one link. So ground is considered as link 1. So though it is connected here, it is connected here, it is connected with the ground, but we only consider it as one ground link. Okay, so can you see how many links are there here? So ground link is 1. Okay, so this is the crank here, link 2, and this is link 3. So this is link 4. So this is link 5. So this is link 6 and link 7, and slider is also a link. So altogether there are 8 links here. Now we need to count how many full joints are here. How many full joints are here? Okay, so you can see the joint 1 here, joint 2, 3, 4, okay, 5, 6. So can you count how many full joints are here? So there is a multiple joint here. So you can see there are 10 joints. Okay, so 1, 2, how many here? 3, 4, 5, 6. Okay, there are 7, 8, 9, 10. So there are 10 joints here. Okay. So now you can apply the condition, whether to know whether this is what will be the degree of freedom for this. So we can calculate from the formula, which we have noted down, based on the number of links here. Okay, so 3 times L minus 1. So L is 8, 9. So 8 minus 1, 7. 8 into 7, 21. Minus 2 into J1. So how many full joints are there? 10. So no half joints. So it is like 21 minus 20. So that means the degree of freedom is 1 for this mechanism. So the degree of freedom is 1 for this mechanism.
Get that again.
Second?
How do you get that joint?
Okay. 1, 2, 3, 4, 5, 6, 7, 3. Alright. Then let us look. Can you see how many full joints are, how many links are here first? Okay, ground is link 1. Okay, so this is link 2. So this is link 3, link 4, link 5, link 6. So there are 6 links here. How many full joints are?
Okay.
Okay, so 1, 2, 3, 4, 5, so 6 and 7. Okay, this is half joint. Okay, so 7 full joints and 1 half joint. So you use the formula. So 3 times 6 minus 1, so 5. So that means 50 minus 2j1. So 2 into 7, 14. Minus j2. j2 1, so minus 1. So it is something like 15 minus 15. So the degree of freedom is 0. Okay, so here now we try to bring the meaning of degree of freedom. So for a mechanism, for any linkages, okay, so the linkages to act as a mechanism, so the degree of freedom should be 1. So if the degree of freedom is not 1, then that cannot be called as a mechanism. Because that means the system cannot move. Okay, and when the degree of freedom is 0, so that means the system is a structure. Okay, also cannot move. Okay, when the degree of freedom is negative, that means it is a preloaded structure. So that means the mechanism is under great stress. So the degree of freedom for a mechanism to act a system as a mechanism, the degree of freedom should be positive 1. If the degree of freedom is 0, it cannot be called as a mechanism, it is a structure. If it is negative, that means it is a preloaded structure. So for any system to act as a mechanism, it all depends on the number of links, the number of full joints, the number of half joints. So we can apply the equation 3 times L minus 1 minus 2 J1 minus J2. So J1 means full joints, J2 is half joints. Okay. So this is just for understanding. So you will never be asked a question on the degree of freedom. Okay. So can you find out what will be the degree of freedom for party? Just try to find the degree of freedom for party. Just find what is L, number of links, number of full joints, number of half joints. So you do probably take few minutes to do this, all the 4. A, B, C, D. I believe all of you have scanned your attendance. Oh, you didn't get your card. Okay. Let me know again later. I'll show you. I'll try to update your card. This is not very important. You just answer the questions. I'll show the answer later. Okay, so the first one, number of links, so you can see ground is link 1, link 2, link 3, link 4, link 5, link 6. So total links are 6. Okay, so number of full joints, so this is 1, 2, 3, 4, 5, 6, 7. So number of full joints is 7. So number of half joint is 1. So the degree of freedom for this is 0. So 1 half joint and 7 full joints. Alright, so the second one, number of links, ground is link 1, link 2, link 3, link 4, link 5, link 6, link 7. So there are 7 links, full links. Okay, so links is the total number. Okay, joints can be full or half. So the only half joint here is the one here. Okay. Then the total number of full joints will be 7. So in this case, the degree of freedom is 3. So this is still a mechanism because degree of freedom is positive. Okay, so here the number of links, ground is a link, then there are 3 links. Okay, so the joints are only these 2. The half joint is this. So therefore, the degree of freedom is 1 here. So M means it's a mechanism. So degree of freedom is positive mechanism. So even here, the degree of freedom is, the mobility is there. So here, the degree of freedom is 0. So in this case, the number of links here, okay, the piston, the slider is a link. Okay, so you have this is link 2. Okay, the disc is a link, then the ground link. So the total number of links are 4 here. So number of full joints are 4. Okay, so 1, 2, 3, and 4 here. There are 2 links here. Okay, no half joints, so the degree of freedom is 1. Okay. Now, most of the time we will focus on this 4-bar linkage mechanism first to understand. So then we can move on to a 5-bar linkage mechanism or 6-bar linkage mechanism. So. Basically a mechanism is a kinematic chain, so it basically consists of number of links, joints can be full joint or half joint, and overall based on the degree of freedom, we can categorize a system as a mechanism or a structure. Okay, so for mechanism, for the system to act as a mechanism, the degree of freedom should be positive. So basically a machine is a collection of links and joints so that it can transmit forces and do some meaningful work. Now this one is the 4-bar mechanism. Okay, so 2 bars has a negative degree of mechanism. So this is a preloaded structure. Okay, this one you have seen. Here the degree of freedom is 0, so it is a structure. So 4-bar mechanism, so you can see the degree of freedom will be 1, and therefore we can consider this as a mechanism. Okay. Now, when you talk about a 4-bar mechanism, so the first one is the ground link. So the ground link, please note all of you carefully. So we'll be using the abbreviations. So there are 4 links, right? So we'll be writing A, B, C, D to represent the length of the links. To represent the length of the links. So D is always your length of link 1. That means the ground link. Okay, and of course your A is link 2, length of link 2. Then this will be link 3, link. Okay, so there is a slight difference here. So length D is ground link, link 1. So always link 1 is the ground link. And in terms of the alphabetical order, so the ground link is D. Okay, so the ground link is the distance between these 2 points. So there may not be any physical link. Okay, there is no physical link, or for some mechanism there may be physical link. Okay, but whenever we say ground link, it is the distance between the 2 points here. So the length of link 2, okay, you can consider this as O. So normally when we write this, so we'll say O2. So this is link 2. So O2 A, then B. So this will be your link 3. So there will be ground link. So we call it as O4. Okay, so this is your link 1 or the ground link. So this will be your link 4. So when we use the alphabetical notation, so this is A, this is B, this is C, and this will be D. So O2 is basically a ground link. O4 is a ground link. Okay, so this O2A you can consider it as a crank. So this is a connecting rod. This is also a connecting rod. All right. So when you go back to the slide. So here, so you have seen this is a crank. Okay. So the link connecting link 3 is can be called as a coupler link. Okay. Now, depending on the how, now in this case, this is the ground link. Okay. So this is created by attaching different links to ground. So when the link 1 is the grounded link. So now in this case, the link 2 is grounded. So this is the case when link 3 is grounded and link 4 is grounded. So there's, depending on the type of mechanism given, so any link can be grounded. Okay, for the mechanism to act, now we talk about the Grashoff's condition. So we have already seen Grashoff's condition. A 4 bar is a Grashoff if at least one link can make a full revolution. So one of the link should make a complete 360 degrees rotation. Then we can call the mechanism as a Grashoff's mechanism. So if it is a non-Grashof means the link cannot make a complete revolution. Now, for the Grashof's condition, so the total length of the smallest link plus the largest link. So S plus L. So the length of the shortest link plus the length of the largest link must be less than or equal to the total length of the two remaining links. Okay, so you are going to use this condition for your assignment. Okay, so we talk about your assignment a bit later. So you are going to apply this because based on this condition, you can choose the dimensions of your link lengths. So that means you will be having some freedom to decide what should be the lengths taken. We don't give you all the links. The mechanism will be given, some dimensions will be given. The rest of the dimensions you can apply Grashof's condition and you can fix yourself. So that means the shortest length plus the longest length must be less than or equal to the total length of the two remaining links. So if you follow this condition, then your mechanism will have a complete revolution. So that means at least one of the link in the mechanism will have complete revolution. And this is the condition for a 4-bar mechanism, okay, to function. Okay, so depending on, you can call the crank and rocker if either link adjacent to shortest is grounded. So depending on how the mechanism is grounded, so if the crank rocker, we call it as crank rocker, if the link adjacent to the shortest is grounded. Okay, you call the mechanism as a double crank if the shortest link is grounded. So, because we are talking about the four links, right? The shortest link, the longest link, and P and Q. So, in between the two. So, depending on whether the shortest link is grounded, if the shortest link is grounded, the mechanism is called as the double crank. Okay? If the link opposite to the shortest is grounded, then we call it as double rocker. So if the link adjacent to the shortest is grounded, then it is simply a crank and rocker mechanism. So this is basically depending on the movement developed. So based on which link referring to the shortest link is grounded. Okay. So for example, let us say your ground link is 3.5 length, let us say. So the shortest link is 1.5 and the longest link is your ground link 3.5. Okay. So the total of this is S plus L is 5. So the length of the two remaining links, P plus Q. So that is 5.5. So S plus L is less than P plus Q. So this mechanism is a Grashof mechanism. So that means this mechanism can function. So at least there is one link in the mechanism which can have a complete revolution. If this condition is not followed, then you cannot have Grashof condition. That means the system cannot be called as a mechanism. So generally when we talk about the real life situation, real mechanism, and when you do on drawings, okay, so the depiction changes. So you can't reproduce the real life mechanisms as it is. So when you do geometrical representation, so there must be some amount of, we follow some similarity, but at the same time, we represent for easy purpose. Now, for example, a simple link is normally in reality it looks like this. Okay, a simple link in typical form is like this, but when we draw, we just draw as a straight line with the two dots. So this is the kinematic representation. So similarly, a simple link with the point of intersection. Okay, a point of interest here. So there's a bend here, so this is represented in the diagram like this. So this going to be a simple link, okay, but with the point of interest. So there's some angular displacement here. So it is not just a simple link like this, but it is bent. Now similarly, a complex link, now you have three links here, so you can represent like this. Now this is a pin joint, so you can represent a pin joint like this. Okay, a slider joint is just represented. So this is the reality. This is the kinematic representation or the way we draw on graphs. So a cam joint is something like this in real situation. So when we do geometric drawings, so we just represent like this. So similarly, a gauge joint. So a gauge joint is represented like this. Okay. So for example, now you can see this is the nose wheel assembly of a small aircraft. Okay, nose wheel assembly. Now this one you can represent, okay, geometrically, depending on the dimensions. When we draw this same thing on a graphical representation will look like this. So basically you have four links here. So this is the crank, link 2. Okay, it is grounded here. So also it is grounded here. So this is a ground link, this is a ground link. Okay, so this is link 2. Okay, so this connecting rod is link 3. Now link 4 is now so there's a link joint here, and this is the wheel which has the movement here. So it can be represented with a link 4 like this. Okay. So this is the real drawing of a nose wheel assembly of a small aircraft. Now the same thing geometrically on a drawing we can draw like this. Okay. Now for this we can find out the shortest length is the dimensions are given here. Okay. So the dimensions are given here. So the shortest length is 12 inch. Okay, you can see 12 inch. Then the longest one is 32. So where is 32? Okay. So this is the ground length, 32. Okay. Then the two remaining links are, one is 30, the other one is 26. Okay. So P and Q will be 30 and 26. So now if you apply the Grashof condition, the smallest plus the largest, 12 plus 32. So this is 32, this is 12. Should be less than this 30 plus the in between is 26. So this condition is valid. So therefore this assembly is, and again the smallest link is, okay, so positioned next to the ground link. So therefore it is a crank and rocker mechanism. So you have seen the description here, right? Okay, so it's a crank and rocker because the link adjacent to the shortest is grounded. Okay, so this is how we can analyze the Grashof condition, and this is the real mechanism. When we draw based on the dimensions, so the drawing will look like this, then we can apply the Grashof condition. Alright, so next you have another one here, the pump mechanism. So it's basically a water pump mechanism. So when you represent this mechanism geometrically based on the dimensions given, so you again will have a 4-bar linkage mechanism. Okay, so this is where there is a movement of the piston. Okay, so movement of the piston is shown here. So the piston can move up and down. So this is your link 2. Okay. So this is basically a slider. Okay, so the link 3, the slider itself is link 4. So the total number of links will be 4. So in this case, there will be 3 pin joints and 1 sliding joint. Okay, so the hub joints are 0, there are no hub joints, so total number of joints will be 4. So you can apply the degree of freedom here. So 3 times n minus 1 minus the 2 times the number of full joints. Okay, so that is 4 minus 1 is 3 into 3 into 3 is 9, then 4 full joints, so 2 into 4, 8, so 9 minus 8, 1. So the degree of freedom for this is 1. So this is basically a manifestation of a slider crank mechanism. Okay, so this is again a cut and trim circuit boards. Okay, so for this, can you just draw? Just to visualize yourself, how you can represent this on a sketch. So all this is background basics. You will never be asked a question on these things. Alright, so I'll just go through. So you can draw something like this. Here is the slider. So link 3 is the cutting blade. So this is the link 2, which is the handle. Okay. And this is the ground link. So again, a 4-bar mechanism. 4-bar linkage. Alright, I just skipped. Now this is a pair of wires grid. So draw a kinematic diagram of this. Okay, I can just show you. So this will be one link 4. Okay, so link 2 is the bottom handle. Okay, so this is shown as link 2. Okay, so link 3 is the bottom joint. So this is the link 4 that connects the top and bottom of the handle. So link 4 is, so this is a ground link here and this is a ground link. So A and B are the ground links.
Except for
X and Y.
Yeah, no link, right?
These are just representations only, visual representations. Now, if you want to develop this, normally for any mechanism, you will be given a figure, you will be given dimensions. Then you need to draw the position of the mechanism. So this is just, as I said, the background mechanism to make some sense of what you are going to do later. Okay, so because we not always based on our geometries based on the real life machines. Okay, so we analyze the mechanisms based on the number of things, a 4-bar linkage mechanism or a 5-bar linkage mechanism, etc. Okay, so all these you don't find in your learning guide. Okay, so this is just to make the subject more relevant to the real life scenarios. Okay, so when we talk about a 4-bar mechanism, okay, now you can see this is the ground, okay, and this is the ground. Now this is your link 2. Okay, so the shaded one is link 3, and this is link 4. So now if you want to look at this, so the orientation of link 2, okay, this is link 2, right? So the orientation of link 2, we write as theta 2. So theta subscript 2. So that means we are talking about the orientation of link 2. So here theta 4. So this is the orientation of link 4. Okay. So then theta 3 is orientation of link 3. But how are we going to? Okay, I just. So now let us say this is the point P. So point P is on link 3. So this is link 2, link 3, link 4. Okay, your ground is link 1. So the ground is link 1. Okay. Now if you take the orientation of this point, okay, now with respect to the coordinate axis here, so the angle of this point we call it as theta. So theta is the angle, but you are locating a point on link 3. We are calling it as point as P. So therefore we write the theta with subscript P to represent. So you are looking at that point and then the orientation of that point. The polar coordinate are the angular coordinate. Alright. So I just close this here. Then we will move on to more practical. And as I said, it's always better for you to work in groups. So if you are sitting alone, please join with others. So at least 2 people together, always can share your knowledge and you can understand things better. Okay. Now, the relative positions we talk about here. So I think what all I'm going to do now, you must have studied in engineering dynamics. So let us consider, this is when we talk in mechanics of machines, we talk about coordinate system x and y. So here I'm writing capital X and capital Y. So capital X and capital Y, this is called the global coordinate system. So global coordinate system is fixed. Okay, so now with reference to this, I take a point A. Okay, please use your pen and pencil, don't take it helps you, because once you do yourself, you'll be much better off. Okay, so what I'm doing, I'm just identifying the point is. So I call this as the position vector A. Okay, I locate another point. Okay, I call this as B. Okay, so this is the position B. So next I draw this. How to call this now? Can you tell me? R? No. Now I am looking at the position of B, right? So I call this as position of B, but I already call this as position of B. So this is my global coordinate axis. Okay. Now this is I am calling the position of B from A. So this is the relative position. So position of B from A. Alright, so now you can, this is basically a vector addition. So position of A plus position of B to A should equal to position of B. So when we write in vector notation, so I can write position of B is equal to, so please note I am writing the vectors, not scalars. So position of B should equal to, so position of A plus position B to A. So this is the vector addition. Now, when I want to know the orientations of this, okay? So now I can say the orientation of point B. So I can call it as theta B. Okay, so I can consider this as theta A. So now, how to find the orientation of B to A? So what we can do is, now I'm having a local coordinate axis. Now my global coordinate axis is fixed. So now I draw a local coordinate axis, okay, which is horizontal to the global coordinate axis x, and similarly, which is perpendicular to the global coordinate axis y. So, oh, you can't see. Sorry. Okay. So here the x, y is called the local coordinate axis. So now with respect to the local coordinate, I can measure the orientation here. So you can draw the local coordinate axis for any point. Global coordinate axis is fixed. Okay, so always we'll be talking about the capital X and Y, the global coordinate system. Small x and y is the local coordinate system. So we need to make sure that the local coordinate system is small x should be parallel to the global coordinate axis x. So similarly, the y should be parallel to the global coordinate y. So the most important point here is that the position of B is equal to the position of A plus the position of B to A. Okay, so this is your A, this is your B. Now, this equation is a vector equation. So now I can take the differentiation of this. I can also write now velocity of B should equal to velocity of A plus velocity of B to A. So please note again, this is a vector equation. And of course, I can also write acceleration of B should equal to acceleration of A, acceleration of B to A. If you understand these three equations, the entire 2 questions related to mechanics of machines are based on this. Okay. I'll go back to the slides. Okay, so the same thing here you can see. So capital X, capital Y are the global coordinate systems. Okay. So point A, the position of this is shown as RA. So the position of this is shown as RB. Now this one is the position of B from A. So you can write RB slash A or textbooks they write BA. So that means the position of B from A. And the arrow is important. Okay, so we are looking at the position of point B but from A. So this one we don't write because this is the global coordinates. So position of B is from the origin. So similarly position of A is from origin. So we don't write BOA. So they are referring to the global coordinate axis. Okay. Now, vector addition, if you see, I have written that the position of B should equal to position of A plus position of B to A. So the vector addition, so RB should equal to RA plus RB to A. And RB, RA, RB to A, all vectors. So don't consider that you can just add the numbers now. You can't add the numbers. It is, we need to look into the scalar notations, x component, y component, okay, or unit vector notation. Then only you can do. Otherwise, just based on the numbers you can't do because we are dealing with vectors, not scalars. Okay, so now the position of B you can write the position of A negative. So if you refer the equation, position of B is equal to position of A plus position of B to A. So now position of B to A can be written as position of B minus position of A. Again, this is vector addition. Okay, so I think I skipped this. Now, please take note of this. This is the beginning of your actual work. Okay? Now, this is a typical 4-bar linkage mechanism. Let me tell you, the textbook is freely available online, PDF form. You can download. And the living guide has all the things which I'm showing. So what is more important for you is that you have to understand that and then develop your skills of doing the maybe drawing the sketches. So later I'll be giving you the dimensions, then you will start drawing the mechanisms to scale. Okay, so this is a typical 4-bar linkage mechanism. So you may just see O2 represents, okay, the ground link for link 2. So number 2, okay, this is your ground link. O2, O4 is the ground link. So the distance between O2, O4 is considered as link 1. Okay, so this is the length of link to O2, A. So the distance from O2 to A is the length of link 2. So length of link 2 is A. So when we use the ABCD notation, A represents the length of link 2. So D represents the length of link 1. Okay. So now the local coordinate system you can see small x, small y. Okay. So global coordinate system is capital X and capital Y. Now the orientation of link 4 is referred to the global coordinate system theta 4. Okay, so theta 2 is again referred to the global coordinate system. But theta 3, if you want to measure, then you need to have a local coordinate system. Because you can't measure the orientation of link 2 with respect to the global coordinate system. So what we do? We shift the coordinate axis to the point here. So we have a small x, which is the local coordinate system, okay, and small y. Now you are measuring the orientation of this link 3 with respect to the local coordinate system, theta. Okay. So whereas theta 2, theta 4, you can easily measure with respect to the global coordinate system. Okay, now the first problem dealing with mechanics of machines is doing the position analysis. Okay, so position analysis means we will be giving you the dimensions of the links, okay, and orientation of link 2, theta. So the length of all links will be given. Then in addition to that, theta 2 will be given. So what you need to do, you have to draw the mechanism to scale and find out theta 3 and theta 4. Yes.
See the length when you mean the x and y coordinates of this length.
Okay, you are free to choose your own scale. You can choose your own scale. And always, you need to start, of course, with reference to a global coordinate system. So it's very simple. You just draw a vertical line, horizontal line, call it as capital X, call capital Y. And you always need to look into the dimensions given. Because based on the dimensions, then you need to choose an appropriate scale factor. Okay, so then it is easy for you to draw the mechanism to scale. Okay, I'm sorry. given the length of the four links. Okay? So that means you know the lengths and you only know the orientation of link 2, theta 2. So now to draw this, what you do is first, okay, choose an appropriate scale. Okay, so you know the length of link 2. So you can draw this. The ground link you can draw. Okay, then you know the length of link 2 and also the orientation of link 2, theta 2. So since you know theta 2 and this O2, you can draw. Okay, so that means link 1 you can draw, link 2 you can draw. Now how to draw link 3 and link 4? Now to draw link 3 and link 4, what you do, okay, you know the length of link 3, right? So you put your protractor here. Choose the length because you know the length L3. So then you draw the semicircle B dash. Okay, so put your protractor here, then you take the length, draw a semicircle. Okay, so the semicircle will. Okay, after that then you go to O4 because you know O4 already. Okay, and you know the length of link 4. Okay, so again measure that, again then you draw this semicircle. Okay, so the two semicircles will, okay, cut each other. Okay, so this point now you can fix as your B. Then you can draw AB and you can draw O4. So this is called the open position. Again, so this semicircles also will cut here, B dash, okay? So this is a cross position. Okay, our mechanism is only O2A, B and B to O4. So once you fix the position of B, then you can again measure theta 4 angle, and also you can choose a local coordinate system now, and you can measure the angle of B. Okay, so the mechanism given to you is something like this. So the R1 refers to the length of link 1, or in alphabetical form it is D, length of 2 is A, length of link 3 is 3, you can R3 or B, so this is C. Okay. So theta 2. So now, okay, I just, okay, the first thing is drawing the geometry, and as I said, the problem is to calculate orientation of link 3 and link 4, theta 3 and theta 4, right? So analytically, for the same 4-bar linkage mechanism, without drawing, without doing any drawing, if you want to measure theta 3 and theta 4, the formulas are shown here. So the formula for theta 3 is this. The formula for theta 3 is this. So where ABCD represents the length of the 4 links. Okay. So for example, if you want to find out theta 3, you need to calculate D. So what is D? So D is cosine theta 2 minus K1 plus K4 into cosine theta 2 plus K5. So what is K5 and what is K4 and what is K1? So they are defined here. So K1 is D over A. So what is D? Link 1 length. A is link 2 length. What is K2? D over C. So K1, K2, K3, K4, K5 all defined in terms of the 4 lengths. Length of the 4 links. So depending on A, B, C, D, you can calculate K1, K2, K3, K4, K5. So once you know K1, K2, K3, K4, K5, then you can calculate this A, B, C. A AB is cosine theta 2 minus A1 minus A2 cosine theta 2 plus A2. So theta 2 will be given to you. So therefore, you can calculate capital A, capital B, capital C. So capital D and capital E. Okay. Once you know all these things, then theta 3 and theta 4 can be calculated from this. Okay. This is a difficult calculation, time-taking calculation. But when you do the same thing using the geometric, okay, position analysis, drawing the sketch, it will be straightforward. You can get the answer theta 3 and theta 4 without doing all this calculation, just by drawing the simple sketch as shown earlier. Okay, so you can see here, just measure once you fix the point B, okay, then you can calculate this is the orientation of theta 4 and this is the orientation of theta 3. So position analysis is much simpler. And this is the position, this is the analysis, okay, this is the graphical position analysis, okay. Depending on whatever the type of orientation, okay, this is the same technique. From the given data, drawing the graphs. Whereas the formulas which we have used, okay, this formula is applicable for only a 4-bar linkage mechanism, which has a orientation as shown like this. So, which has a orientation like this. If the orientation changes, if you have a 5-bar mechanism, the formulas will change. You need to derive the formulas. So therefore, the graphical position analysis is always easy and straightforward. And in the exams, we are only doing those things. So you will not be asked to do the analytical solution. So analytical solution is what we have done, this one. I'm not going through the derivation of these equations, so you can read from the learning guide, and it is not required. It's quite easy, not difficult. Okay? Okay, so now the practical aspect. I give you the data, start doing it. So your first problem is, okay, so for every problem, okay, you will be given the mechanism shape, or how the orientation of the mechanism. So now we are dealing with the 4-bar linkage mechanism. Okay, so link 1 has a length of, let us say, 6 inch. Link 2 has a length of 2 inch. Link 3 has a length of 7 inch. And link 4, 9 inches. Okay, it doesn't matter inch or centimeter, you choose, doesn't matter. Okay, unit is not important. So theta 2 is given as, okay, 30 degrees. So now our job is to calculate theta 3 and theta 4. Draw the mechanism scale and measure theta 3 and theta 4. As I said, always helps you. You have your own freedom, but it always helps to bring people together. Everybody must do, but you can consult each other. And yeah, and no more, don't make your smartphone smarter. So I always try to do this. No, all this you can get from the learning guide and also from the textbook. The most important thing is practice. I don't want to scale you, but normally more than 50% students do get high distinction for this distinction of high distinction. But always there will be 10 to 5 to 10% people fail this. I don't want to 5 that percent, I want 100% pass. So I don't want to scale you, but 50% students do get high distinction for this distinction. But always there will be 10 to 5 to 10% people fail this. I don't want to 5 that percent, I want 100% pass. So I don't want to scale you, but 50% students do get high distinction for this distinction. for 60% marks in the term exams where you are plotting this. These type of, this is a very simple one, 4 mark. In the exams you will have 6 mark. With some practice you like it. And don't think that your drawing will look like this, which may not look like this. It's just the guiding figure. So you have essentially a 4-bar mechanism. So first step, draw x-axis, y-axis, global coordinates. You can identify the open position and cross position, but only measure the angle for the open position. Any doubt, you can call me, I'll come to you. So theta 2 is 30 degrees. So the orientation of link 2. So theta 2 is 30 degrees. Okay, you can do normally these things using CAD very easily, but that is only for your assignment. So you still have to practice this because in the exams you are only doing okay on paper and using a pencil. Okay, once you choose your x and y axis, then fix link to at 30 degrees. So measure 2 units and put at 30 degrees. That becomes your scale factor. So what is your scale? You are using the same dimensions? Yeah, so you use only. So once you fix O to A, so now put your protractor at A measure the length of ring 3, that is 7 units, then draw a semicircle. So then measure the 9 units C. Okay? So from 4, 4, draw the semicircle with the 9 units.
Yeah, same. Why is that?
Correct? Yeah, I said it will be different. So measure theta 3 and theta 4. Okay, let me tell you honestly, you must practice here. And if you want to do it, more complex things, so you get this. Let's connect
Oh, it's the. Yeah, it's the close. That means the other side of the other intersection.
I see, I think half the class completed. So measure theta 3, theta 4. So theta 3, you have to choose the local coordinate axis and measure if required. So this will be theta 4. So I give you another 3-4 minutes to complete. So what are the answers for theta 3 and theta 4?
89 89
Okay.
then 117
How much? Same thing?
half
91.
I think around there I think 是 ratio 不是98又要钱这应该是对的，因为它加起来应该是89应该差不多6应该OK 没有，我画的是完全跟我的说不理那个过程。
So anyone need papers?
你差那个，因为它不是跑掉的，是跑掉的。我觉得它的比较好，它的本身也是滑出来的。对啊，有时候有些。反正我写，我可能有个书，我可能有个书。Yeah, I think that one better. Yeah, I thought like one module.
Okay, so your sketch will look something like this. Second, yeah. So normally 5% error is acceptable. So, for example, in this case, you okay. So you can see the theta 4 is about 117. So it's okay. You get 116 or 118. 119 is acceptable. But let me tell you, as you move forward, your error will be very, very less. First, maybe there's some error. But as you continue with other examples, error will go down. But if you want to do the calculation using analytical method, it will take you much longer. Okay, so the open position is theta 3 is about 117. Okay, theta 4 is theta 3 is about 88 or 89. Okay, and theta 4 is 117.
So is it necessary to draw the cross section?
This is just for only this example. Later we know.
So exam, let's say the answer draw, we don't need to.
No, exams you will not be asked like this. This is the beginning. No, you have a lot of time. So before that, I'll be introducing you the assignment. Then you will understand what you get more. No, it's interesting. It's not difficult. It takes some time to catch up.
So assignment is based on drawing.
For assignment, you can use CAD.
You scan. Oh.
All right, now the time is nearing 8:30, you can go for a break, 20 minutes. 8:30, you start.
Yeah. Wow. Actually, I want to tablet. I also thinking of buying tablet.